Hi, this is Adam Baker from Affinity Energy. Today we've got a webinar about 7 unique ways to optimize solar trackers. Over my career, I've been involved in about 1,000 megawatts of solar tracker installations at various sites around the United States and internationally, and worked with probably 6 or 7 different solar tracker manufacturers. So I've seen a lot of systems, all of which have worked pretty well. But in every case, there have been opportunities that I have seen where we could do some integration that would allow the overall site to just operate better. Affinity Energy is a control systems integrator based in Charlotte, North Carolina. We do work all over the Southeast United States as well as nationally. And since I've been working here, I've been involved with solar projects really all over the spectrum, from small 1 megawatt sites all the way up to 550 megawatt sites. So I've probably been involved with 4,000 or 5,000 megawatts of solar over my career. So I've seen a lot of different systems, and I've seen things that work well and things that don't work real well. One of the good things is also a bad thing about trackers in general. Trackers, like many solar site components, are designed to operate independent of the control system. It's an island of automation where there's some integration from monitoring, but the tracker system is designed to work independently of whether or not there's a plant control system or not. And the good thing about that is that if there's a communications loss or some event where the tracker will never be in a situation where it doesn't know what to do. So that's a positive for the tracker, but these days the communications and reliability is extraordinarily high, so the likelihood of that happening is pretty low. And it also means that the trackers don't really know whether the rest of the site is running or not, and the site doesn't know if the trackers are running or not beyond what you see on your SCADA screen. So if the systems aren't communicating together, there's really no good way of getting some optimization or some benefits of having the systems work together. So we talk about optimizing solar output. It's not just the trackers that are designed to be independent operated systems. The inverters are really designed to not necessarily have a plant control system above them. The MET stations are designed to be just data collection systems that feed information up to SCADA. So all of these standalone pieces of equipment, they can all derive increased value by having them work together and taking information that might be valuable to the other system from the first system and taking advantage of integration that doesn't commonly exist at solar sites. So we can make some small improvements to how the trackers work that will derive a whole lot of benefit and save you money. So as we step into the first of the 7 ways that I have to optimize, we're going to talk a little bit about a common misconception in solar. I hear from customers a lot that the most important thing that they believe that is important with the tracker system is that the trackers follow the sun as closely as possible. I think most people would say that ideally they would want the trackers to continuously move to follow the sun so that you can really optimize the output from the modules. So along with the perceived need to track as closely as possible, the downside that comes with that is just the nature of the mechanical engineering around having bearings supporting the tracker system. Every time you try to move the torque tube, there is a force of stiction where the bearings are trying to stay still and you're trying to force them to move. Overcoming that stiction is a little bit of wear that will happen on the tracker every time you do that. So every time you stop and then start the tracker movement, you're going to have a little bit of wear and tear on those bearings that support the tracker system. So fewer moves means less stiction events, which means potentially longer life cycle of the tracker system in general. If you step back and do the math, it's really unnecessary to track that closely. So as the Earth rotates, the sun moves 1/4 of a degree every minute. That's about 15 degrees per hour. My original back-of-the-envelope calculation said that if, as a data point, if we waited and tried to do a 5-degree tracker move, that would be a move every 20 minutes. And you'd go from 2.5 degrees behind the sun to 2.5 degrees ahead of the sun. And if you take the cosine of 2.5 degrees, that keeps the potential output from the modules at 99.90% of their rated output. So you're at less than 0.1% output loss due to misalignment with the sun if you're doing a 5-degree move every 20 minutes. 20 minutes is less than the frequency that most trackers move. Most of them move every 5 to 10 minutes from my experience. So if you look at the losses in the system overall, if you have 6 megawatts of DC installed, there's probably about a 1% loss due to module mismatch. There's about a 1% loss just from the conductors carrying the current. There's resistive losses in the collection of energy. And then 1 to 3% is fairly typical for the amount of dirt and accumulation, the soiling losses you have on the modules. So a 5% overall loss in DC power is not uncommon. So trying to keep 0.1% module output from the modules is probably overthinking, over collecting, or overworking the system. So with a typical tracker site design, you've got a DC-AC ratio of somewhere between 1.1, 1.15. Those are pretty typical. So that translates to a 1 megawatt inverter having an extra 150 kilowatts of excess DC power. And when you take out 5% loss for the components we talked about on the last slide, we still have 5 to 10% of DC excess capacity. So an 18-degree move, or 18 degrees off of ideal, is a 95% DC output from the modules. So if you were to be 18 degrees behind the sun, you'd have 95% of rated output, and that would still be within the DC-AC ratio losses from the site. So now we could actually do a 36-degree move from 18 degrees behind the sun to 18 degrees ahead of the sun and get full output from your inverter throughout that entire time period. And that translates to 1 move every 2.5 hours. So in summary, moving the panels as infrequently as once an hour will still get you better than 95% of the DC energy, which is in excess of what the inverter can convert anyway. So 5-minute, 10-minute, 15-minute moves to keep the tracker pointed very tight are unnecessary. So why worry about trying to keep the trackers pointed as close as possible to the sun? So bullet number 2, avoiding DC overvoltage. Early in my career, I saw a lot of sites where we had to put in some electrical, mechanical switching so that when the DC voltage was getting too high and the inverter was at risk of tripping, we would drop out some of the DC in order to manage that DC voltage and keep it in spec for the inverter to take. With today's inverters, they're a little more tolerant of wide DC voltage ranges, but there still is an upper limit to what an inverter will accept and operate in MPPT. So if you've got a very high DC-AC ratio, you're more likely to run into trouble here. And controls can definitely help. So if you've got a tracker system and your DC voltage going into the inverter, well, that's a parameter that we monitor from SCADA and can integrate with controls. If we see that the DC voltage is getting high, we can command the trackers to move a little bit ahead of the sun, which would reduce the DC voltage, bring it back into range. So your inverter output remains the same, and you're using the ability of the trackers to manage your DC voltage going into the inverters. Again, today with most inverters that I see, this isn't really a big concern, but with some less expensive inverters, it might be an opportunity for you to keep the DC-AC ratio high and keep the inverter output running when it might otherwise trip. So moving on to bullet number 3, I think this is the easiest to justify and lowest hanging fruit is to take the opportunity to wash the panels for free. We've talked in the past about soiling being a problem in solar sites. There are various forms of soiling that can happen, pollen, dust, leaves, etc. All these things happen throughout the year. You'll have different soiling types in different areas of the country. And by and large, when the losses get significant enough, there's a difficult decision that has to be made about whether or not you roll a truck to go out and wash the site, rinse the dust and dirt off the modules, or you send people out with a brush or a cleaning system to go and clean the modules. Those are both expensive events to go and have to do in order to recover the energy that you're losing due to soiling. But in most of the country, we have rain events periodically, and we can take advantage of the rain events when we've got a tracker system and controls working with it. So if we know that the generation output from the site, it's early in the morning, it's late in the afternoon, or it's an extremely overcast day, we've got low generation coming off the site anyway. And moving the trackers to an orientation where the rain can do the most good for just rinsing the panels off is something that can be easily integrated into the control system. So you may lose a little bit of energy if you're not pointed far to the west at the end of the day when there's a rain event, if you move the trackers to something closer to a flat position, but the energy lost might be easily recovered in one single day if you can reduce the amount of soiling by 5 or 6%. If you live in an area where snowfall comes, snowfall is actually the best way of cleaning soiling off a panel. A lot of tracker systems will leave the modules parked at a fairly high angle of incidence at night so that some types of soiling sources don't adhere to the panels. They sort of, if it's their leaves, the leaves are less likely to get stuck to the panels if they're tilted 45 or more degrees. But if it's going to snow at night, I'd actually recommend using a little bit of snow accumulation on the modules, maybe an inch or 2 inches if it's light snow, to accumulate, and then when you move the modules to a higher angle and the snow slides off, you're actually getting the full benefit of somebody going out and effectively hitting the modules with a squeegee to clean the soiling off it. So as the snow slides off, it takes all the dirt and accumulation with it. So you can use snowfall to really get a good cleaning and reduce soiling. If we've got a Met station at a site, and all the solar sites have a Met station, the control system can know whether or not it's raining, whether or not it's snowing. So it's a fairly simple exercise to integrate what we know from the Met station with the control system in order to affect the tracker system. Bullet 4, here in the southeast, vegetation is a persistent problem on solar sites, and I see companies who are willing to come out and do the vegetation control, basically mowing the lawn. With fixed sites, it's more of a challenge to mow the lawn because you've got an edge of module which is maybe specified to be no less than 18 inches from the ground, but the structure underneath it is going to leave you less clearance than that, and it's just difficult to get mowing equipment under that. So if you've got a day in which you're going to have vegetation management come out and clear vegetation from a site, it's pretty easy to just put the tracker in vegetation mode, point everything flat. And the great thing about trackers is when they're pointed flat, you still have a generation as long as the sun is up. It might not be optimized and pointed at exactly the right angle, but like I said before, if you're off by a few or 10 degrees, you're not losing a whole lot on the energy side. So just moving the trackers so that there's an easy way of parking them makes it a whole lot easier and quicker for the vegetation management people to come in, do their job, and move on. And you might be able to save some money on the O&M side there. So bullet number 5, preempting wind events. Almost all trackers have a wind sensor associated with their controls so that they can detect high wind conditions and move the modules to a near flat position that will reduce the mechanical stresses on the structure due to the winds loading on the panel. But the problem with that system is that it's not predictive. The wind sensors get the wind speed as it exists at that moment in time and can't really predict when there's a wind event coming, whereas with something like a Met station or an RSS feed, the SCADA systems often know what the upcoming weather is for a site, and they can anticipate that there's wind that should be coming in an hour, and you can start to move the modules to a safer stow position. So as the wind starts to build, you're getting ahead of trying to stow everything. With some tracker systems where not all the actuators will move all at the same time, It might take 15 or 20 minutes to get all of the modules from an orientation where they're pointed maybe due west to a wind stow position. And certainly we can have a whole lot of wind build up over 20 minutes that might not give you enough time to stow everything. So we just want to get ahead of the curve. If we have the information to know that the wind is coming, we can start to move towards a safer position with the tracker system even before the wind gets there. Item number 6, just monitoring how the actuators are performing and detecting when there might be a binding event. So the good thing again with trackers is if a tracker actuator stops working, the failure mode is we're still making energy, just not as much as would be optimized. But predicting when a tracker actuator is going to stop working is not as difficult a task as you might think. What I have recommended to do is to look at each actuator's current. What current is an actuator drawing over the course of a day? And whatever that highest current is indicative of whether or not there's high loading on that actuator to move the tracker. You don't need to continuously monitor it. You just need the value that it was at the maximum over the course of a day. And in normal operations, the tracker actuator that demands the highest current should change from one table to the next over time. So if it's moving all around the site, that's sort of normal. But if you're seeing the same tracker having a high current draw over and over again, it's the same tracker every day, that's probably indicative of some binding on the tracker system, and that could come from a number of sources. In the southeast, I see quite a bit of vegetation, vines and grass that will grow up into the mechanical structure of the tracker, and that will cause some binding, but also as the bearings wear, or it could be something as simple as somebody leaving a piece of equipment out in the field that's just impeding the tracker from smooth operation. All of those things are a trigger to say, okay, let's roll somebody from O&M to go out and investigate what's happening. To know and send them to the specific tracker actuator that's having the problem is going to save you a whole lot of time and money. The last issue I see with tracker systems in general is people tend to want to collect all of the data that they can and historize it. Tracker systems, various tracker systems from different manufacturers have a widely varied amount of data that can be collected from the tracker system. And towards the end of my career, one of the sites that I did, we actually counted and had 28,000 data points per megawatt at the site of just tracker data. So of all of those points that were available, there were several hundred that were useful, but taking all of those data points into a historian would have been prohibitively expensive. So filtering out what data is valuable, what data that you can turn into actionable information to do O&M and keep the system efficient and running, that's important. Back in my automation days, we always estimated that an analog point it costs about $10 to implement as a life cycle cost. That's the cost of the software to support that point, the integration of that point into the software and the HMI and the historian. When you add all that up, it costs about $10 to have an analog value in SCADA. And if you have 28,000 points, it's just prohibitively expensive to collect everything. And quite frankly, most everything is not necessary to determine whether the system's working well or not. Some of the things that I see, the time it takes for an actuator to execute a move, I don't see how that's valuable. If it takes longer than normal, I don't know what you would do about that. It's actually more indicative to say whatever the highest actuator current was is more indicative of whether the system is working well. Average motor current per day is another value. I don't know what the average really buys you. I just want to see what the highest point is for each individual actuator. You don't really need to know each individual actuator's position. And this is the most common thing is I've got 20,000 actuators on a site. So how do I make an HMI screen that shows me the position of everything? All I want is a list of the actuators that aren't pointing near where they're supposed to be pointing. Don't tell me everything that's good, only tell me the things that I need to pay attention to. So it's not always obvious how to figure out what data is useful and what data is useless from a tracker system, but certainly Affinity Energy would love to help you work those out. So max current per actuator, tell me the 5 actuators that have the highest current draw over the course of a day, and run that report every day for 2 or 3 weeks. And if their same actuators are showing up over and over again, then you've got a potential O&M issue that's upcoming. And you have the time to plan on what to do about it when you know that it's coming, rather than waiting till there's a failure. Give me like I said, any tracker that isn't within a few degrees of where it's supposed to be pointing. That can be valuable. The tracker might think it's moving if there's a feedback mechanism, but it isn't actually moving. Maybe the tracker has gone beyond its movement range. If there's like a rack and pinion sort of gear system that would move the tracker, often if they move too far, then the teeth disengage and they won't move back when the tracker actuator tries to move them back. So if you have the feedback, whether the tracker is pointed somewhere near its commanded position. If it's way off, that might be something to look at. And lastly, I'd always recommend, if there are alarms that are being generated by the tracker system, those you certainly want to have integrated into SCADA, because the tracker system is going to alarm when there's an actionable need to go out and service the system. So the last thing, just about tracker data in general, my thoughts are, just because data exists doesn't mean it needs to be on the screen. We've got a sample here of an inverter screen that I use frequently, where there's a whole lot of data, but there isn't a whole lot of information. There's just too much clutter on the screen to know whether or not this inverter is working well, and it can be 10 times worse with a tracker system. So if you boil down to just the points that are valuable, that give you the information you need to figure out where the problems are, it's going to make the system more valuable to you. You'll spend less time finding problems that'll jump right out at you. So if you've got a site with trackers and you have a plant control system, I'll say that it doesn't matter what tracker that you have. The integration between controls and the tracker system isn't hard. It's just that most people don't invest the time and money to do it. 95% of the time, trackers running independently are fine, but there's probably 5% of the time where you can be taking advantage of a tracker capability to optimize the solar field overall. So again, there's a small opportunity cost to do this integration up front, but certainly I would expect the return to be many times that over the life cycle of the plant. You get more energy output, better control of the maintenance activities and prevention of downtime, and you'll just get a system that performs better overall. So the integration of trackers into the site control and SCADA system, it has some additional cost, but it's a very small cost relative to overall project cost and the cost of the control system. And it really will give you the opportunity to derive benefits that will last through the life cycle of the plant. So there's a small opportunity cost, but the value that you get over the long term, I think, is really worthwhile. So if you have any questions or want to talk a little bit more about solar trackers or solar in general, feel free to reach out to me. My contact information's on the slide. Best way to reach me is via email, abaker@affinityenergy.com, or you've got my direct desk phone, 704-766-2060, and I'm at extension 135. Thanks for tuning in, and hope you got some value out of the webinar today. Take care.